like sitting down, wherever, like it's not like an uneven deal.
How do you choose your moment?
I don't care, it doesn't matter. I'm just saying, like,
Well, I have a question.
Or click on the
Can we
ultimate
reassess how many days?
Go like 9
How does that work?
Right.
Tomorrow, that we know that.
Right, but
That's
you don't cook, it's hard, but they'll cook till they.
your days end progressively earlier and earlier,
Yeah.
mine do
That's
not.
how you get that.
Right, but they went that way.
Could we possibly,
Okay.
okay,
Yeah.
yeah.
What's that? What's that? No,
Yeah.
my days don't.
So when is convenient for you?
3 o'clock on Mondays and Wednesdays, right?
Yeah,
Okay.
yes, so just Wednesday. Why are you leaving?
So, here's where we are in our understanding, okay? Here's where we are in our understanding. Here.
I didn't think I was supposed to be here.
What's that? All right.
Some people don't really go down those
Join us, please.
websites.
So, here's where we are. The way that I understand that this works looks like this. So, if you have a tuning fork, so if you have a tuning fork, if you bring the tuning fork, what happens to the little tuning fork tines? What happens to the little tuning fork tines? Do they literally move in and out like this? Okay? So, did we see them actually move in and out in the demonstration? The demonstration works like this. So, if these are moving in and out 256 times a second, okay? If I set the little strobe light so that it is slightly offset from there, right? What happens is it catches the tuning fork tines as they move in and out only occasionally. So for example, the light comes on, they're here, the light goes off, they move out, and then some fraction of in, and then the light comes on. And then the light goes off, and they move out, and then some fraction of in again, and the light goes out, and they go this way, and now they're here, right? And the light goes off, and this time they move back to here. So because the light is only catching them so often, we're not seeing a full in and out. We're seeing like boom, 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 boom. That's why it looks slower, yes.
Can you reiterate what you just said? Or rephrase it? Oh, okay.
Did you not see the demonstration?
I saw part of it.
Okay. So that's why it looks like it's slower. So here's the question. If I were to set the strobe light, okay, if I were to set the strobe light to exactly 256 flashes per second, what would the tuning fork look like it was doing? Check your neighbor now on this one. If I were to set it exactly to 256, what would it look like it were doing?
Unofficial date.
Yeah, what?
A little slower, a little faster. If it was the same, then it would be exact.
What would you see?
It's going on one to the same amount of times per second. Stationary.
All right, so what would it look like if I set it to 256? What would the tuning fork look like it were doing under that strobe light conditions?
Nothing.
Not moving, that's right, because every time like the light would come on, the light would go off, it would move the same distance, the light would come on, the light would go off, right? And so you would see it look like it was not moving at all. Is that okay? Does that make some sense? So that's how we're able to see it progressively like that. Is that cool? All right, so how does that sound get to you at all? Right? That's the question. How does the sound even get to you? right? What does the sound wave have to move through to get to you? It has to move through the air, correct? And so what happens is, as this tuning fork moves in and then moves out, what does it do to the actual air particles that were next to it? It bumps into them, true? Now, what then happens, okay, so then it bumps into these air particles and pushes them, so where are they next? Then they're there, true? Does that make sense? And then in the next moment, the tuning fork moves back this way, and then it comes back this way. But in that time, these air particles have done what? They bumped into the next set, true? Which then does what? Bumps into the next set, which bumps into the next set. And what we end up with is a pattern that looks like this, where we have an area that's all bunched up, and then an area that's all spread out, and then another area that's all bunched up, and then another area that's all spread out. And so what we see is, as this goes back and forth, it's sending this little bunchy part. This bunchy part is moving through the air, right? So it's a bunchy part followed by a spread out part, followed by a bunchy part, followed by a spread out part. Does that make some sense? Can you visualize that as an idea? Mr. Treater, will you hold this, please? Where are you, Paul? No? Will you hold this, please? It's not here, that's so weird. And so I can simulate this. If the tuning fork is over here and I start sending waves this way, can you see a bunchy part followed by a spread out part followed by a bunchy part? So it's like, you guys with me on that? So these are called, they're a different kind of wave. These are called compressional waves. They're also called longitudinal waves. Okay? So this is our idea. So the question today is, how fast? Is that cool? We don't know how fast. Yes?
So, like I found a view, there was like talking about like transverse waves and longitudinal waves or
Yeah.
whatever they're called. So transverse, like what we did yesterday when it was like, it goes like from one side to the other, but it's like up and down, like when it's like perpendicular.
Mm-hmm.
And then longitudinal is when they're like parallel.
So the transverse wave is the kind of wave where the vibration is perpendicular to the direction of the velocity. Okay? And in this one, the vibration direction is parallel. So yes, that is the difference.
What?
It's not helping. All right, so how are we going to do this today? Okay, how are we going to do this? Well, as I suggested yesterday,
No, that's not what happened. If you was drilling with your right hand, I'll take it, and I'll over and I knock the ball. I'm gonna be saying this a while.
So, when you head to your lab station, okay, you gotta make sure that you have a tube, okay? Someone's gonna have to hold the microphone out front here. That's not a big deal, okay? Someone's gonna have to hold the microphone out front. All right, the easiest sound to make that can be loud enough for the microphone to hear it, go down and come back, is a snap. Okay, so we're gonna snap. Now, here's what I see. Here's what I hope that you see. Okay. So, what's going to happen is, when you snap, it's going to trigger the microphone to start recording when it hears that snap. But this down here, this is in like nanoseconds, so it's like in a small amount of seconds. And so it should give you, and then it'll be like, oh look, there's your snap. So you should see something that looks like that. Then, the sound is going to travel down, hit the book, and come back. Okay? You guys with me on that? This is what you are looking for. Okay? This is what you are looking for. Now, in general, okay, because we're doing a sound lab, you should like keep it down a little bit. Use your inside voices. Does that make sense? Because if you're yelling or you're talking loud, then you're going to trigger other people's microphones, and that's annoying. Is that cool? So try to use your inside voices. So how are we going to figure out the speed from this? Okay? How are we going to figure out the speed from this? Well, what two things do you need to know? The distance. Do you think you can use a meter stick and figure out the distance? Okay. How are you going to get the time? So what you're going to need to do is figure out 2 points on this little wave pulse that are identical. Let's say you use the very front. We'll call this T1 and T2. So if you do analyze, examine, you can put your cursor on this and it'll just give you the time. Okay? So to get the time, you get the difference in these two. Does that make some sense? So you need a distance and you need a time. Do you feel? You guys all right? Yeah. So when you're just laughing like this, all right, because I'm standing up here, I feel like you're laughing at me.
I'm not.
I know you're not.
Okay.
Okay? But that's what it seems like to me. And because I'm a little bit insecure about it, it makes me start to feel bad, and then it makes me start to get angry, and then we don't want that. All right? Does that make some sense? Because consider, like, if you were up here trying to do something, and I was back there just giggling away, do you see how the messages could be construed a little bit?
Yeah.
Okay? So this is what I would like you to do today. Does this seem somehow reasonable? Okay? That seems like something you should be able to do? So, we're going to have to put the lab stations together a little bit. Okay? Every lab station is going to need a Lab Pro, that's a green box. You're going to need the power source for that and the cable to connect it. And then you're also going to need a microphone. All right, so I'm going to give you a number. We're going to cruise to your stations. You're going to build the lab stations, and hopefully you're going to be able to do this. Does that sound reasonable to you? If there are catapults at your station, I want you to move them up to this front area here. You need to take them with you today. Does that make some sense? So stop back by after school, get your catapult, and we'll go from there. All right? Sound good? All right, let's count. Let's count to 7. 1, 2, 3, Patrick Henry, 4, 5, 6, 7. 1, 2, 3, 4,
2, 6.
7. Mr. Reed? 1, 2, 3, 4, 5, 6. Michaela, 7. Noah, 1. Charlie, 2. Henry, 3. Calvin? 5, 6, 7, 1. Move to your station now. Let's get these set up. No. What are you doing? because the clock lasts too long.
David, do you live?
The lab grows.
I saw you. I live right by you. I just found out. I saw you. I think you were cutting your grass. What? Really?